Wednesday, so so has everyone able to access the open review for reading assignment 3? Because some people say they cannot input their review, but I guess there's no issue right now. Cool. Okay, so today we'll start our module on talking about generative models, in particularly models that are very effective in structural design of protein structures, such as diffusion models. Can everyone hear me? So this lecture the next two lectures will mostly focusing on the machine learning perspective, and following that we will be having dedicated lectures on how we use these models for design the structures of proteins, and there will be one guest lecture on Rosetta full diffusion and frame flow, which is the most powerful, one of the most powerful generative model for protein structure design. All right, so I think we briefly talked about generative modeling in the first kind of machine learning bootcamp, but in the short term, like generative model, unlike supervised learning, where we try to predict certain labels from input features, here we kind of learning to just directly fit the data distribution without necessarily the existence of a label. So we can consider that assuming we're given some data samples as which can be considered to be maybe IID drawn from the actual distribution. And the goal here is to learn a parameterized model P theta such that we either implicitly model P theta, so we can accurately approximate P theta for the underlying distribution. We want the P theta to be as close as possible to the true data distribution. Or alternatively, we want to train a model that is able to effectively sample from the distribution without being accurately predicting P theta, the value of P theta. So both realm of methodologies have been used to train generative models, and but as mentioned, the key question here is whether how we kind of able to represent these probability distributions, right? So we talk about language models in previous class, which is one of the simplest way of defining a parametric model for explicitly modeling the probabilities, which is factorize it with some kind of Markov assumptions, which is commonly, the assumptions commonly exist in sequence type of data because we have this kind of left to right ordering, and it is maybe okay to assume that ordering and conditional independency given that ordering. So this kind of model is effective in modeling like natural language processing data. There's also normalizing flow models, which we'll go into detail in the next week. But in a high level, this is kind of try to learn a invertible function between px and pz, such that if we can represent pz with some parameter family that is easy to use, we can directly invert through that network to get the function of p theta x. But today we're going to start with two approaches. One is variational autoencoders. The other is energy-based models. Because these are previously kind of effective models for under certain types of assumptions. But I think these are also very important model to know because it closely related to the motivation of diffusion as well. So variational autoencoders, it belongs to, in a high level, it belongs to a type of family that relying on a latent variable model, where basically instead of just having the observable features from the given data, we also assume the existence of some latent variable, which there is some unknown underlying joint distribution between z and x, but we're only able to observe x in real world. So such kind of z, I know that's a little bit abstract, but in real world you can consider z, one type of z is kind of this latent concept, right, of features. If we're modeling human faces, we could consider z being inherently like the gender, like, or the eye colors, right? These concepts can be, they're the existing variables, random variables that coexist with the image, just that we don't necessarily observe them, or they're not explicitly given, but they're closely related to the distribution of x. So one motivation of using these kind of latent structure is these X are basically relying on the infinite possible, like continuous high-dimensional input space, and to learn these high-dimensional representation and probability, the model kind of rely on a lot of data. So the intuition here is if we can find some low-dimensional variable z, which kind of corresponds to kind of the high-level features and structures of the data, which might be easier to model with the known families of probabilities, which are easy to sample from, and it's less likely to subject to kind of overfitting or curse of dimensionality. We might be able to leverage those structures in the data. Another intuition is kind of this, considering we talk about this kind of clustering architecture, clustering algorithm, which is also a family of unsupervised learning, where we try to kind of fit the data with some number of mixture of Gaussians. We're assuming that the data can come in from different modes, where each of the modes can be represented locally with some Gaussians. So an intuition here, we can represent the likelihood by first considering the latent variable being the center of the Gaussian, and then compute the likelihood of the point belonging to that cluster. So effectively, we have this hierarchical representation of probability, where we can easily factor that into this kind of weighted average or mixture of Gaussians. But here we have kind of a predefined number of Gaussian mixtures in the data. But we can consider the variational autoencoder. We kind of assuming kind of an infinite number of Gaussian mixtures in the space, which will be learned by the algorithm. And there is no kind of predefined centers or predefined number of clusters. And we just try to use kind of most general representation way of representing these latent space, such that we can explicitly model the conditional probability of x given z. And we can also try to model the joint distribution. However, when we're actually running sampling, right, we're actually modeling, we would try to kind of learn the likelihood of the data. We only have the observable part, which is the data. So the objective functions ideally should be maximizing this marginal probability of x, where we do this kind of marginalization out the latent space. However, this marginalization part is really intractable or very difficult to compute if we want to precisely compute it for every x, right? So VAE or variational inference, so there's kind of a model for efficiently modeling these kind of conditional sampling with latent structure. We call it variational inference, where so instead of like kind of solving this very intractable marginalization, we try to approximate with a sum posterior, which we can approximate with a neural network. So we can condition on each x, we can sample in z, and we don't have to focus on all possible regions of z. We can use a network to focus on kind of very concentrated region of z, and we can effectively estimate these likelihood function of the data by using this variational inference trick. So in the high level, this is one way of deriving these effective objective function, which we call evidence lower bound or ALBO. This is the final loss function. But in high level, the trick they're using here is basically multiplying this term with a q phi over q phi, which is 1. And by introducing this term, we're kind of able to exchange the log function from outside of the expectation into inside of the expectation by using this Jensen's inequality. So originally, this log of the expectation is kind of intractable to compute, but by multiplying this q theta and dz, we can consider this term as the expectation over q phi, and this Jensen's inequality can exchange this log term inside to this integral. So at the end, we can also use this log term to kind of break this part into two parts. The first part is directly can be written down as the expectation of the log of the p theta, which p theta is the kind of reconstruction of x given z. And then the second term is the expectation over p z over z given x, which is effectively the KL divergence between these two terms. We can consider this kind of as regularizing your latent space, regularizing your latent sample generated by the network to be as close as possible to the predefined prior distribution of Z, which is kind of usually Gaussian. So we call these loss function as confidence lower bound. One thing you can see that there is an inequality here, so it's definitely kind of smaller than the actual likelihood. So that's why it's kind of like the lower bound of the actual likelihood functions. And if we look into more specifically, we can look into the loss, that the first loss, if we interpret this as basically for any given x, any given data point x, we try to see if we can reconstruct the x from the encoded latent space Z by applying the decoder and encoder. So we call this term a reconstruction loss. And the second term is the regularization term, which penalize the encoder such that the encoded latent space condition on x is very close to the prior distribution. So we can call these two networks, these two neural networks, to learning the conditional probability, the encoder and the decoder, which is very explicit from its expression. So you can see, you might see this diagram a lot when we look at VAE, right? So you basically have a given sample data x. During training, we sample it directly from the training data, and we pass it through an encoder network, which gives us a latent representation Z, and we also have a decoder network, which for any given representation Z, we can use the network to invert and generate the probability over X. So this ALBL has an alternative derivation, which also tells you why this such confidence bound is tight. But in the high level, we don't want to go over the details now, but in the high level, it's similar derivation by taking the base rule in the first step. So after this derivation, you could, at the end, see that the first term is exactly the same as the ALBL term we derived from the Jensen's inequality. And here, everything is equality because we're not exchanging out the log in this time. We're directly operating in the log P space. Here, you can see this additional term that makes it, in inequality, is this additional KL divergence between the true posterior of Z given X and the approximated Z given X, which is kind of not possible to exactly write down, but we know that if we optimize this perfectly and we have a perfect approximation of this true posterior likelihood, this term will go to 0. So this is kind of one way of interpreting the ALBL, the tightness of ALBL, that with the hope of optimizing this ALBL, we get a true approximation of Z of given X as well, and then we will have exact likelihood maximization loss. All right, so in practice, what it needs is basically we try to train these two networks, right? And particularly because we need to parameterize the conditional probability, and most of the time we can use this Gaussian family, which is very, very easy to use, and we just make these kind of Gaussian assumptions, but you could definitely consider other types of families to model these probability of Z. So a trick that is used here is instead of directly condition on the so to represent a Gaussian function, we need the network to output a mean and a variance of each dimension of Z. So instead of directly drawing sample from that mu and theta distribution and taking the expectation over that, and kind of common trick used in RL to reduce the variance of this estimator is the reparameterization trick, which instead of directly sample from these two, we kind of reparameterize the Z with respect to kind of the normal distribution, epsilon. And in the training time, we just need to sample the epsilon, which controls all the stochasticity. And we multiply it by the sigma and shift by the mu, so as we can kind of unbiased, variable Z. But we're only stochasticity only come from this single normal distribution draw. So there is more general derivation showing that these two are equivalent, but just to remember that this trick helps reduce the variance a lot in our estimation, because we're kind of estimating a distribution while sampling from it. And there are additional tricks that apply here, because when we sample it, we also go through the network, and but a lot of this can be rewritten with the chain rule. So at the end, this estimator will effectively have lower variance than the kind of the original estimator. All right, so any questions so far? So, but basically, considering we have if we're introducing kind of this latent space, and we're introducing a Albo estimator or variational inference perspective, such that during training, we'll be able to maximize the likelihood in an approximated way by using this variational inference trick. So for any kind of latent z and x, and any problems where we have a latent structure z and input x, we're given only the data of x. We can use this trick to achieve efficient approximation and optimization of the likelihood.
Is there anything called just the autoencoder?
Yes, so the autoencoder do not have this sampling perspective. It's only focusing on learning a low representation z, space z, where the z is not regularized with respect to any probability. So the autoencoder is used to do dimensionality reduction. So we only care about reconstruction. But it's not useful for sampling because we don't guarantee any sampling accuracy in that we're not maximizing the likelihood when we use it as a generative model. So I forgot to mention about sampling perspective, but when we actually sample from the variational autoencoder, you can consider basically unconditional sampling being directly sample z from the marginal distribution of z, which we ask it to be a univariate Gaussian. So we sample a noise z, and then we use the decoder network to sample a example x. And that's kind of the unconditional sampling procedure for variational autoencoders, where you just try to generate a sample that is close to your training data. And the denoising procedure is you could add kind of an imperfect image. Maybe you kind of crop part of your image out, or you noise your image a little bit, and you fit that into this network, and getting a noisy kind of a latent representation, which again, always remember that the z here is a random variables, so we always need to parameterize with a Gaussian probability, right, with the predicted mean and variance. We always sample a sample from z, whether or not we condition it on a x or not. So condition on x, we have a Gaussian parameterization, condition on x, and we have z given x, and we can also derive a example by using the decoder. In that case, it's kind of like the denoising use cases, but it's like not exactly proved to be the denoising, because if during training time you don't give it imperfect x, the model would not explicitly learn to denoise. There's also a denoising autoencoder training where you explicitly ask the model to do denoising, where the training procedures is different by you. The input x will then be artificially cropped or noised, and you want the model to explicitly reconstruct from the noised image. But again, that's not. It can be considered as kind of increasing the adversary robustness of the model, but it's not necessarily guaranteed to be a good generative model. And this variational perspective here is trying to tell us how we can effectively leverage the training data x and the structure of x given z and the prior information on z to train a generative model that maximizes the likelihood function, which originally is intractable. And we'll see this later being used in actually diffusion loss derivation as well. So the concept can be a little bit abstract, but basically you can consider that knowing that we can't explicitly sample the joint marginal distribution of z, so we have to condition on x and converting that probability based on the given sample x and taking the expectation with respect to the x instead of with respect to all possible z. Okay, so the next very important family of the model is called energy-based model. We kind of repetitively mentioned this word multiple times previously. But if we reflect on the models, the other models that we mentioned today, like the autoregressive model, the normalizing flow model, or the variational autoencoder model, we kind of have already predefined a existing structure for the model. although these structures are kind of we try to define it as generalizable as possible, it's still kind of restricted. So the intuition of energy-based model is kind of to allow a free definition of the probability. So as long as you could represent the function, represent the P with certain function, it shouldn't be restricted by the predefined structure. So the kind of the original motivation of energy-based model is to come up with very flexible architecture and flexible definition of the probability, where we just make sure that we can use a very complex even deep learning or techniques to model different functions, and we have to make sure that functions we propose can be converted into a legitimate probability. So what is a legitimate probability, right? So the probability density functions or categorical distribution, if in the discrete space, are basically these density functions over the input space, and it has to be non-negative because we don't know what a negative density function means in probability, and it has to be normalized, which means that it have to be sum over to 1 if we kind of marginalize on all possible input space. So the first one is very easy. We can come up with a lot of different functions to enforce this positivity. But the second one is more trickier. And luckily, we kind of have these. We basically want to define a way of normalizing the score, assuming we kind of give a positive class. We're using this function that is known to be non-negative. We want to have a way of converting this non-negative function into a legitimate probability space by basically dividing it with this normalization term, which we call the volume of the G of theta. So this term is not tractable for any function, but we know that this function is sometimes tractable if we for a certain given types of families, we know we have to solve these integrals, and we have analytical form of such functions. So for example, these are the families that we kind of know what the volume can be. And of course, for this one, you can exactly write down the likelihood function without relying on the energy-based model. But again, we're confining ourselves to a limited set of family again, and that's not ideal. And to make it slightly more general, if we know that we have two given probability that are already probabilities, we can consider mixing them together by either kind of taking the weighted sum of these two probabilities or doing kind of a product of normalized probability. So the normalizing function will be between these two probabilities. But still, this is kind of not still the most generalizable way of defining a function. So the energy-based model come up with this general intuition that I just learned whatever function of f theta, which I just want to make sure it's positive. And then I take the exponent of that and then define this function p theta over the expression form here, where I take the exponent of f theta and then normalize out by doing this integration over the possible x, and which we usually call it partition functions, or again, it's also a value, or it's a normalizing constant under these exponent of f theta. And this way we can show that this is, again, always a density function. And the reason it takes exponential is, I think, mostly because we call it energy-based model. So in the real world, it's actually closely related to a lot of the statistical physics function, where kind of we consider thermodynamics, considering the definition of energy in physics, and this term has close relationship with the statistics, how physics compute a lot of important statistics such as like entropies. And there are additional numerical advantage of taking this exponent. Basically, you kind of want to capture these large variation in probabilities, and you don't want to confine you to kind of very narrow space. And a lot of the very well-performed, behaved distribution families are closely related to exponential family as well, like Gaussian. So it does not solve the problem of writing up the likelihood function. I just give you the definition of energy-based function. I'm not saying that this is something that is very easy to compute. Again, it has exactly the same issue with all the with all of these marginalization tricks here. So, so this part is not very easy to compute, and a lot of time we just choose not to compute it, or we try to come up with like smart ways of approximating this, or try to just don't use it, or try to get rid of the z. So there's the fundamental reason of why this is hard to compute is it kind of has also these scale of curves of dimensionality where you can't just simply enumerate all possible x, especially if you're in a high dimensional space. But as I mentioned, some tasks do not require using the z, and which can be, and in a lot of these cases, we can exactly sample from it without even knowing the exact energy function or the normalized probability underlying. Sorry, we need to know the energy function, but we don't need to know the underlying probability or density function. So one such example is, for example, anomaly detection or denoising. If you contrast two examples, you can basically get rid of the denominator when you do this subtraction. So you can think of anomaly detection as we just want to evaluate if something has a high density in our distribution, right? So we can basically, if we have a fitted unnormalized score function, or sorry, not score, energy function of any given sample, even though it's unnormalized, we can still compute the ratio between the density of two samples exactly, because by taking the ratio, we get rid of the normalizing constant. And that can give us information about which sample is likely to be coming from the distribution or not, or basically the directional information of whether the sample belongs to this distribution or has a high density in this distribution. And similarly, denoising has a similar indication, but I will get to that later when we talk about diffusion. But it's not like fully impossible to learn it still. Like if you really want to learn it, there is some way of approximating the likelihood and try to compute or maximize the likelihood in a very approximated way. And but the basic intuition here is, like even though we don't necessarily accurately estimate the z, we know that we just want to contrast. We want to come up with a law such that if we're not just maximizing the likelihood, we're not just training the f of theta that is maximized on the training data, but at the same time we make sure that the rest of the distribution, which is what the normalization constant is doing, is compressed down to a very low level. So this normalization constant here is considered like the density normalized in all possible sample space, right? So if we're given some training data, if we blindly optimize for f of theta on the training data, we still can't guarantee that outside of the training data, this z won't take unnecessarily portion of the probability. So the intuition here is we want to increase the f of theta on x train, but at the same time decrease the z f of theta on the regions that are away from the x train, or basically push down the wrong points. So it's kind of like contrastive learning, and the name of these training procedure is called contrastive divergence, where you basically doing a contrastive algorithm where you have a data sample and you have a current network that you're training and you're sampling with your current network. And what we try to do is just to take a step such that my training, the score function that the energy function that I'm learning is maximized for the training data point, and is minimized on the sample that I'm drawing. And by iteratively running this, we could at least getting some closer to the normalized, true likelihood function that is defined by the energy function that we're learning. So you can see that this procedure still requires sampling from the current model, which is kind of also like a variational inference where we have to sample using the model. So what the model is doing, but again, we don't have the exact kind of likelihood of the model, so it's not. So we don't have kind of a variational autoencoder type of sampling procedure here, but instead because we know that we're learning a energy function which inherently defines a probability space, we still can come up with some algorithm such that we can use the algorithm to use just this learned energy function and still roll out samples in the space that kind of approximate what the true distribution is. And again, the trick here is, again, like try to do it for pairwise, basically taking steps. And for each step, because we have pairwise points, we can contrast that and we can get rid of the z, such that we still have unbiased estimation of the ratio. Is this something look similar to you? Who want to try? Like we've actually talked about something that's very close to what's described here. Basically, sorry, I forgot to mention the method. So we can basically define a Markov chain Monte Carlo in the input space, where we just start from some random guess or like random starting points, and we try to like go around, explore around in the space, and once we sample the next point that we want to jump to, we take a look at the predicted energy of the current point and the point that I'm jumping into, and to see if that point has higher energy than mine. If that's true, we can move to the point, but if it's not, I still have some probability of moving to that point, and that probability depends on kind of the ratio of the likelihood of the 2 points. And we can do this iteratively, such that basically you kind of try to making jump towards the high energy space, but you rely on some kind of random jump, and this is kind of Monte Carlo approach. Does this remind you of any algorithm that we talk about in the semester? State space? So not exactly, but I think it's related to one of the optimization algorithm that we talked about previously in a discrete space. All right, if not, we can go to the advanced version of this. So remember that the first one, we're blindly doing jumps with this noise, right? So this can be very inefficient, because if you don't have... Yes, exactly. That's exactly Metropolis Hastings. Yeah. Yeah, and we talk about that in the discrete optimization class as well. The Metropolis Hastings. Yeah. So the Langevin dynamics is advanced version or improved version of the kind of the random MCMC, where we kind of know if we have access to this energy function, which approximates the underlying distribution, we kind of know that we should be able to also access some estimates or statistics of the underlying function. One such statistic is the gradients, right? We basically have some different local information about the directions that I can go, such that my energy function can be improved. So instead of doing kind of random jumps, there is a Langevin dynamics procedure, which is defined by at each time we're doing this kind of jump, but the jump is guided by the energy function that I learned right now. So it's kind of like if you're in the force field, you're kind of you can following the force towards the direction that you want to move, but there's also like random motions in thermodynamics in space. So kind of each step you're going is not only decided by that force, but also some random noise. So the Langevin dynamics is kind of like the combination of the gradient information from the underlying energy function that we currently estimate, and also a random noise that is usually dependent on, for example, temperature and in actual physical space. So this will give us always a distribution at each time. But basically, each time you jump, you're sampling still from kind of a neighborhood distribution. That distribution is defined by the gradient information of the energy we're learning. And that gradient information, or actually the gradient with respect to this density function, is called the score of the probability. So we can see that because we're taking the gradient with respect to the x, and this normalization constant or partition function is a constant that does not depend on x, because we marginalize out x already, this gradient function can be unbiasedly estimated by taking the gradient of our energy function. So even though we don't have the exact solution for the density, the normalized density, we can still estimate the gradient of the density, or the log of the log of the density with the gradient of the energy function that we're learning. So basically, we could consider that the sampling procedure is how we leverage this information we can exactly compute with the current network to mimic a sampling from the actual distribution defined by the energy-based model, parameterized with our current model. And does this remind you of something we implemented earlier in the semester as well? Anyone want to take a try? I mean, this is not exactly the same as what we implemented, but basically using the gradient information to tell you where to go. Does it sound familiar to any of you? Oh no, like, that's a bad news because this is in our P set or our homework. No one want to give it a try? So it starts with the letter G. Yeah, Gibbs-Swift gradient. Yeah, this is kind of like Gibbs-Swift gradient, right? So instead of doing, searching over all possible neighborhood, we use the gradient information from our objective function, and we're making jumps based on that objective function, and we're also like rejecting that with kind of Metropolis Hastings procedures. So the similar thing here, like you basically have this gradient information, and you also have the randomness by, instead of doing Metropolis Hastings, we're doing this kind of Langevin dynamics by basically perturbing around your next step. So you kind of still have stochasticity in the sampling procedure. And as we're doing this, I mean, this randomness actually helps us to jump to a global optimum better, because if, for example, if you only blind follow the gradients, you might also get stuck in some like local minimum or anchor point. But having this additional noise, kind of you're jumping more drastically and searching along the space. So we're kind of moving towards effectively this Langevin dynamics is also like heavily inspired by physics as well, and it's also kind of used to approximate the important physical statistics. Okay, cool. So, any questions so far? All right, so we're moving forward. So now let's go back to take a look at what all of these training, what all of these algorithms are doing, right? They're all kind of trying to directly maximize the likelihood given the data, and they're taking all different approach to approximate the likelihood given the data by either parameterize it with autoregressive model in language model, or parameterize with an invertible model called flow, normalizing flow, or we parameterize a latent space and also use decoder and encoder to define the likelihood, approximate the likelihood using elbow. And in the energy-based model, we can't explicitly maximize the likelihood, but we have some loss that we define that approximately optimize the likelihood. But all of this is try to directly maximize the likelihood function of P, which you cannot get around by especially for energy-based model, it's really difficult to mess up with the Z. So the pros is we're exactly maximizing the likelihood, which is the principle of machine learning, and it's kind of when you're comparing models, you're operating on this likelihood space, which is a unique and defined probability space, which makes the model maybe likely more principal. But the counts is that either you have to play with different kind of specific structures, right, like the Rayleigh-Sholto encoder or invertible network, or if you go with the most generalizable energy function, you kind of lose track of the exact function because of these intractable partition functions. Alternatively, like there's GANs, which we don't talk about in this class because we kind of not seeing it be super useful or like not performing as the state of art right now in the molecular space. But in general, like in short, it kind of consider again some adversarial structure during generation, which can be giving you like samples that have higher quality, but it's also like very unstable and are subject to some like mode collapse issues. And it's not a principled way to derive likelihood. It's not relying on the explicit kind of likelihood or inherently maximizing likelihood at all. So instead of directly going for likelihood or come up with this kind of non-principled way of generating samples, is there something that we can use to enjoy the flexibility and the kind of still underlining likelihood distribution in some sense? So that comes the definition of this kind of score functions that we talk about in Langevin dynamics, where basically if we know how to estimate the the gradient of log p, we know how to sample from the distribution. And that's not relying on the normalization constant as well at all, because we kind of already showed that the score function does not depend on the normalizing constant. And it has kind of some physical meaning. For example, like with kind of these force field or like any field that it can be underlining those energy functions. So you can consider this kind of score function as kind of a directions or vectors or the field of vectors, where at each point you have some directional information towards where you were going, where you're moving to next. And by following these vector field, we were able to use, for example, Langevin dynamics or other sampling procedures, which still allowed us to approximately sample from the distribution. And So this is just a visualization of like what we effectively can be learning instead of almost feeding on these P of X, which is also high dimensional and very hard to define. We're operating over a much better kind of log P space, which we might be able to think of way of learning from the data more efficiently, and which is kind of the alternative approach to training. You can consider somewhat of training energy-based model without learning an energy function. So we just talk about these contrastive divergence training of energy-based model, right, where we still try to train this f of theta, which relying on this kind of approximation of the z by this contrast divergence and iterative MCMC, which is super expensive during training. But however, if we could look at the alternative way, take alternative view of this function, we don't have to exactly like maximize p theta, but instead, if we can learn the probability, if we can use a parameterized function to parameterize the vector field or the score function of a given distribution defined by the data, we will still be able to, train a generative procedure only driven by this parameterized model, and still get unbiased sample from the distribution. And this training procedure do not rely on very extensive MCMC. By just kind of considering the very naive thing here is like if we have all of the training data and if we're able to get the gradient of the p of theta in this that closely match the actual distribution, the log of the gradient with respect to x for the actual data distribution. And we are able to match this on like all the points that have non-zero weights. We should be able to have a good kind of approximation of the vector field that may enable us to sample from it. However, still like p data does not have explicit form, right? We only have the samples, and there's no analytical form of p data. But luckily, we can kind of try to solve these problems with a lot of mathematical tricks, like using, for example, integration by parts. And at the end, we actually we can see that it's very surprising that the final like score matching laws of the energy-based model does not rely on the mathematical form of p data, and we can rewrite the function into a function that only relies on the current f of theta, which is the model that we're trying to train, and the trace of the second derivative of that data. So I think that the math in behind is quite lengthy, but I think what you don't need to memorize all of that, but basically remembering that if we use the mathematical form here, we're able to approximate the score matching loss on the given data point exactly. And a good thing about this is it does not limit to just energy-based models. So it hypothetically, like anything that you have data with, you could always apply this function. So, I mean, there is kind of the realm of thought that maybe score-based model has potential to even generalize beyond the energy-based model. But I found this energy-based model, like intuition or motivation, being like very intuitive and kind of interesting. So we kind of take that approach from as an introduction to diffusion. But we can get the high-level idea is we have these kind of stain score function, which is defined by the Jacobian of the function that you're fitting and the gradient of the function that you're fitting. And if we're able to maximize this term on the data, we might be able to compute a fairly good approximation. All right, so therefore, the original score matching, denoising score matching model, which is kind of the precedent of the current diffusion model, kind of making use of these score matching properties to kind of approximate a data distribution without explicitly try to recover the likelihood. So what it does is kind of you have some probability density defined by the data, and we just sample from the data, and we can estimate their score functions by basically try to hypothetically, inherently it is kind of matching you're kind of learning this vector field function that matching these log of the p data, which is defined by the data points. And the loss function they're taking is kind of very naive. It's basically using these like Euclidean distance of these two vectors, and we just kind of take the average like L2 norm or Euclidean distance between the two vectors, and that kind of is shown to be enough in terms of approximation. And again, like you can interpret that as the feature divergence between two probabilities. But again, like p data is kind of hard to represent. So through this complex like integral by part, you get this alternative score matching loss again, which you can see that these two terms only rely on the S of theta, which is the model we're training. And the expensive part is this kind of Jacobian of SE. So you can see that although this is kind of a nicely analytical, we have an analytical form of the score matching loss, it still has certain limitations, right? Particularly the biggest limitation is the computation of these like Jacobian, basically the trace of the Jacobian. So yeah, I think we don't need to go to very details, but we can consider this as kind of taking a partial differentiation with respect to the data, which is very, if you have like really high dimensional data, it's not a very trivial thing to do. You know, so this particular step, if we have like dimension of d, we need to do like OD back propagates to compute the trace, which is the kind of diagonal of this matrix, which is not ideal. Like we always want to scale up, and we have usually like very high dimensional, the high dimensional space, right? So like this step is really bottlenecking, and therefore we have to come up with kind of some other way of solving this in a more scalable fashion. So interesting, there is a earlier work called denoising score matching, which instead of directly going towards fitting the score on just the original like data points, they kind of try to introduce it's a noise version of the original distribution, where basically if you use this q theta instead of the p of x, where the q theta is the posterior of p of x, assuming that you're kind of adding some noise over the original data. So it's kind of like the yellow distribution here. And the interesting thing is, if we give up on exactly estimating score on just the data points and instead taking a noise of the data and try to solve for the scores estimated on this noised version of the original data distribution, it turns out that the estimation of the score on this noisier distribution is easier. And what I mean by easier is we don't need to compute the Jacobian anymore. Again, like what it's doing here is basically taking the original data, which is giving the data distribution, and apply certain noise on top of the data. And again, you now have a noised data samples, which is, again, inherently some distribution, which defines as Q theta distribution. And if we're solving for the score matching loss on these sets of new data, we don't need to compute Jacobian anymore. And if we consider that the noise is very, very small, like you can get close to your actual data, then even if you have like a little bit noise in the distribution we're looking for, but if you sample from this distribution, you're kind of likely to reproduce the original distribution to some degree. Of course, the more theta you add, like the further away you are from the original distribution, so then you will have kind of a low quality score estimation. So ideally, you want the theta to be super close to the data. But unfortunately, like if theta is like 0, you have infinite variance in this estimation. So this algorithm, like you still cannot have perfect estimation. So this is kind of the derivation. I leave it in the slides in case anyone is really interested in looking into how it's derived. But the interesting thing is if you're estimating the score on this noise version of your data, then the final loss that you're computing does not rely on the Jacobian anymore, and the final loss can be rewritten as a predictor of the noise that you're added to the predictor of the noised data given the clean data. So basically, the score function at this noised Q theta equals to kind of the projected the noise of is related to basically the noise between the noise that you injected to the original data. So you can consider the problem now becomes a denoising prediction, where what the procedure is you sample a true data point, and you on this sampled true data point you apply some perturbation, and you get a noise data point, and we just need to train a denoising neural network such that the network is predicting the x of I minus x divided by the sigma square, which is kind of recovering the noise that we're training. So yeah, I think this is a bit counterintuitive, but if you check all the math, it gives you this kind of a interesting result that the estimation of some function of the underlying function does not need you to access that underlying function, and it now becomes the estimation of the noise. And this is again like assuming the perturbation is Gaussian, but you could come up with other way of corrupting the data, and you will be still able to come up with some similar derivation, but that's not Gaussian, but which may not be as elegant as this one. All right, so so we're kind of arriving from deriving the score function of the corrupted posterior probability of Q theta, which is kind of what is used in deriving this term. So in fact, you could basically interpret this term as like sample x and sample a noise, and then just train the model to kind of estimate the noise that was added to the product. So this is kind of the score matching loss, but at the same time, it's kind of, you can interpret this at some level of denoising loss as well. Interestingly, there's other work called Twitty's formula that kind of, which directly studies the denoising procedures, and when they kind of directly looking at these denoising procedures of recovering x from x tilde, it arrived on a similar result where the optimal denoising strategy is to follow the local score, basically the gradient at the q theta sigma. So kind of, like if you approach it this way or the other way, they kind of meet in the middle, and it basically remove the reliability of explicitly modeling the p over x. But if you only have sample of x, you can still estimate this by adding noise and predict the noise back. Okay, so these are just kind of Tweedy's formulas derivation, but essentially you can rewrite these noise posterior with some like base rules and convert it back to the original score function, and then take the expectation and this kind of log trig, and that will give you kind of very similar derivation at the end. All right, so now that if we train kind of a score function, we will be directly, like, as I mentioned, we can actually apply the Langevin dynamics procedures using the the trained score function, and we just need to follow the scores, and this is kind of like the, so this is kind of like as if you were able to access the ground truth underlying function and take the Langevin dynamics on that energy-based model. If you again want to add back the noise into the Langevin dynamics, which originally has that stochasticity, we additionally takes this additional step, which we add kind of additional Gaussian noise at each step of this Langevin dynamics. But effectively, kind of, if you add this noise, it will help you kind of going to through a more non-deterministic path compared to these kind of just directly following the derivative, and you will see that we actually get a more kind of balanced sampling and more like Gaussian-like result when you add this noise back. And from the sampling perspective, this is kind of helping us. All right, so this is the exact procedure for Langevin dynamics, but again, it looks pretty similar. Instead of using the original log p in the energy-based model, we try to estimate. Here we directly use a score function to approximate the gradient of the log of that function. So we no longer train a network of the energy anymore. We instead train this network of score, which is fitted by predicting the noise. All right, so to summarize, the original, the very early version of score-based generative models come from these kind of underlying observation that we're able to estimate a score for a given underlying probability, especially if that's a energy-based model. And by learning that, we have sufficient information to do Langevin dynamics, and which gives us a generative model. And it is trained with the score matching loss, where you, at the training time, you sample a data point and you sample a noise, which is just one Gaussian noise, and you just try to do denoising at that local area. Of course, this is much scalable than the Jacobian version of the score matching, but there is also some pitfalls of these model. The first of all, it's kind of, the score is not defined in the exact data manifold, because as we mentioned, if the sigma is approaching 0, you kind of have infinite variance, and it's kind of not possible to closely, directly estimate the log p. So we're operating on a little bit noised version of the log p. Secondly, if you look at what you're training, right? Assuming these are the data distribution, if we're applying some noise to our data distribution, we're only kind of looking around in the very limited neighborhood of our data. So remembering that even though we're fitting the vector field, we are not actually exploring all of the space, because we're only focusing on the small neighborhood of the data by adding that sigma. And the more sigma we're adding, the more inaccurate we get with this approach. So in the original denoising score matching, where they kind of pick a particular noise to add in a local data sets. We're only focusing on this very narrow neighborhood of the entire space, and knowing that we're relying on the neural network to generalize to all the space in this data distribution. And what we're learning is essentially like part of the data in the space. So if we only rely on the generalization of the neural network, it can have very terrible estimation outside of this region. So even though our estimation is like close or very close in the neighborhood, in the language dynamics, we usually start from noise, and that noise is not guaranteed to fall into the region that your model generalized really well. So it has this kind of inaccurate generalization behavior, unfortunately, especially in the like almost close to noise region. Okay, so and similarly, it's kind of having some issue with a mixing rate when there are multiple modes in the data. So this motivated kind of in the next version of denoising diffusion models, which is already, you can see some preliminary structure of what we use as diffusion nowadays right now. So basically the idea here is instead of using one noise, you try to include multiple noise level. So with the higher noise level, you're exploring in the kind of a broader neighborhood space, and we're getting these corrupted data distribution at different noise level, and which will be able to estimate the score function at different noise level. So you can consider that basically for a given pictures, we can iteratively applying applying noise at different levels. So at the end, we kind of get basically a fully noise out data, which is very close to kind of the random at the end. So instead of training one score matching functions in the given x, the local neighborhood of given x, we ask the model to also condition on the noise level that we're adding. So we're kind of using the model, using the same sets of parameters, but we're able to adapt to different noise and let the neural networks to generalize, to learn to fit the score at a different noise level. And we're taking these different noise level, taking the loss of the original score matching loss at different noise level, and we're adding some weight in between, in front of it, such that at the end we're maximizing or optimizing this weighted score matching loss from different noise level. Knowing that if you add more noise, as mentioned earlier, your estimation of the score will become worse and worse. So basically, if the noise is very strong, you're kind of in a very bad estimation of the actual like vector field of the true underlying function. But that's okay, because we're also defining a new way of doing this sampling, the language dynamics, called annealing language dynamics. So essentially, you kind of start with a very noisy and like non-accurate estimate of the score, but you're also giving it a very high noise when you do this language dynamics. So you're making big jumps already, like with higher randomness, and you're using this kind of coarse-grained score function to also explore around. And once you take some initial steps, you use that to initialize the second language dynamic steps. And as we're kind of, this first step gives you, although not perfect, but some information towards the final distribution. You kind of start the second language dynamic step. We're using the new scoring estimator after the first step. And this time we try to reduce the noise a little bit, because we now have a better estimate of the score. So this procedure is repeated, such that at the end we're gradually approaching the area of where we have high quality estimations of the scores, such that we can use a smaller noise in the language dynamics to jump around. And by repeating these procedures, we kind of, at the end, we're gradually approaching the final distribution that we're aiming to. And these procedures called annealed language dynamics. So instead of using a fixed like ground emotion noise, you kind of have this noise that also varies with the noise level that you're learning. And the kind of the intuitive way of choosing these noise is try to have your, like, the distribution you're jumping to have some overlap, to have some overlap with each other. So ideally you have some geometric progression on this noise, and this L is kind of can interpret as the number of new Benjamin dynamic steps that's taken until you jump to the region that's really close to the clean data. So now we kind of go into kind of these. When you look at these sampling procedures, like it kind of reminds you of like a sequential, Monte Carlo jumps, right? So this is kind of this is the way that if we're starting from denoising score matching and just try to increase the vector field, the resective field of what we're observing when training the score matching models, we come up with these formulation of noise scheduling and weighted loss. But if you kind of look at the DDPM papers or the blogs, they usually start from alternative interpretation, which again is kind of similar to what is describing here. Basically, you can consider what we're doing here is making these consecutive jumps in the space. Like each jump, and each time we're jumping with kind of like a certain distribution that defined by the score, and which is the noise, and some noise that we're adding back, right? So each jump is kind of like a jump in the MCMC. So the alternative interpretation that the phenomenon paper like DDPM used is to directly define these noising and denoising procedures with kind of a Markov with like a MDP, such that you're kind of taking some basically interpreting these like Benjamin dynamic steps as the iterative procedure of removing noise and making these Markov jumps that only condition on the each. So each time you jump to the next T, you kind of condition on the previous T, like where you are in the previous T. And we can also take the similar interpretation. In the forward process, right? Basically, if you try to consider the process of adding different level of noise, you can also consider this iterative Gaussian noise adding procedures. Like basically, at x0 you add some noise, and x1 you add another step, you add some other noise. By doing this Gaussian corruption through multiple steps, you're also defining kind of a noisy procedure that is able to give you different level of noise. So if you look at the perturbation procedures, right, you can define you can basically define some some mean and mostly the variance that you're usually like the variance that you're jumping to. So you can basically each time of the jump you can define this conditional Gaussian probability, which describe like at each single step how the Gaussian noise are added. And when you do multiple steps of jumps, so you can also get the joint likelihood of this final the joint likelihood of this chain that will define this joint distribution of sampling basically the time series. Yeah, if you consider each times as like a time step, each step as like you give it kind of a time step, you can consider this kind of as a series of points that defined by like this trajectory, and you will also be able to compute the exact joint likelihood of this trajectory. And what's more, if we look at the multi-step transitions, because each step is a Gaussian, right? And it's very easy to basically compute the distribution at xt directly by composing these Gaussian distribution. So instead of like computing it t times, this forward process t time, we could directly compute the mean and variance at all different t's by just using these formula, which gives us like a very efficient way of doing this perturbation and basically defining a way of perturbing your data into different levels of noise, and that level, the noise is defined and determined uniquely by this t. Okay, so so if we take this perspective by considering everything as kind of a Markov John, there's a forward process and a inverse process. Basically, like you can kind of think of this forward process of doing this perturbation as if in the original score matching paper, and we're doing this multiple times, such as like at the end, when we add noise to enough level, it ended up becoming very close to a random noise. And the sampling procedure will be basically try to invert these procedures from like this pi of x, which we usually kind of consider that as like some initial noise distribution or source distribution. And the problem becomes like how we, given this kind of known forward process, how we invert this process with multiple Langevin dynamics jumps. So the DDPN paper basically skips all of those kind of score, the definition of score with this kind of derivation of like Jacobian, like the gradient of the underlying energy phase function, that directly say that I just want to define these Markov chains such that I've kind of learned a function that knows how to jump back from the noise to the data. And by each jump I'm defining a conditional transition probability, which is characterized by a neural network, which is the denoising, the diffusion network that we're learning. And we're tackling this problem by doing it kind of as like a multi-step denoising problem. Of course, this kind of xt given xt minus 1, the exact inversion is intractable because you have so many possible way of like doing forward jumps and going back. But again, like you can consider this as kind of a if you look at marginalize out all possible trajectories, right? This is exactly like what we're trying to marginalize out in the variational inference. We basically take the variational inference approach to learn an approximation of this inverse process by using neural networks to explicitly learn the probability distribution of xt minus 1 given xt, and we're training these distributions with a loss that is very similar to the variational loss we've seen in the variational autoencoders. And again, we have to make some assumptions because like our model family is only capable of learning what we define. So again, we're kind of taking this kind of Gaussian parameterization for this the inverse process, which is proven to be quite effective. So with both the forward and backward process defined, we'll be able to write up this joint distribution of the forward and backward trajectories. So the problem then now becomes this kind of hierarchical. You can consider the problem as like a hierarchical variational autoencoder, where instead of doing one step latent embedding, we have this multiple encoding and decoding procedures, where the encoding procedure is a fixed or like a known, like a given procedure by like we define this noise level and the timestamp, so we know the exact encoder already, and the goal is just to train the decoder, which is reused one neural networks that takes as input the x and a t, or the t can be like basically telling us about the noise, and we use the network to predict these decoding procedures, which involves multi-steps of decoding. Okay, so we kind of talk about VAE at the beginning of the class. This is kind of like adding additional like latent variable on top of the Z1, and basically all the way up to the end. And the training loss that they derive is again like very similar to the elbow, where you kind of approximately try to maximize the likelihood of x is 0. But in the high level, the loss will ended up looking like the expression below. So it is basically we try to rewrite our variational inference loss. At the end, we'll be ending up using this loss here, where we're only relying on samples from the clean data and samples from noise.